say that the stress or the momentum flux at the surface is given by a bulk formula. So it's C times the wind speed times the flow component. And we have one for radial and one for azimuthal. And consistent with our linearisation, we will simplify these down to be that K du dz at the surface is simply C times the wind speed times U at the surface. C is the drag coefficient, sorry, I should have said. And similarly for V component. At that point, we are almost done. And we find our solutions for U and V that they are the real and imaginary parts respectively of this function omega. And in the case of U, it's multiplied by this factor that integrated wind. And omega is given by this formula. You can see we've got the e to the minus 1 plus I on z on delta naught. Delta naught is a height scale, 2k on I. If we were doing the Ekman spiral, that would be 2k on f. So we've got a modification there. And chi is this dimensionless number, which is given by this formula. So, what else can we say about this? A couple of things that are different to the Ekman spiral. We've got I instead of F near the centre of the storm. If you think about the tropics, F is say 5 by 10 to the minus 5. I is much larger, 10 to the minus 3, somewhere of that order. And so this means that the boundary layer is much shallower than you would normally expect in the tropics. Also, the inertial stability increases towards the centre of the storm. At a few hundred kilometres radius, it's fairly close to being F, so it's 10 to the minus, several times 10 to the minus 5. But as you get near the radius of maximum winds, it increases very rapidly. And as a result, the height scale decreases very rapidly, and that is why the boundary layer becomes shallower towards the centre. The other thing is we have this fact, in the Ekman spiral, the amplitude of the U and V is the same, but in this case, the amplitude of U is larger. Within the I, where dV dr is close to V on R, they're about the same, but outside of the I, the amplitude of the radial component is actually somewhat larger than the amplitude of the azimuthal component.
Still, I'm wondering the relationship between this depth, Ekman,
Yep.
scaled by the Ekman, and also the inflow layer.
Okay. You can actually take this formula and work out what the height, solve for U equals 0 and work out the depth of the inflow layer. Or similarly, you can solve for say the depth of the first wind maximum by solving for dV dz equals 0. In practice, the depth of the inflow layer turns out to be about 2.5 times delta. So, rule of thumb, 2.5 delta is pretty close.
My point here is inflow layer is decreasing like this,
yeah.
But still, I think it's very gentle compared to the changes of the absolute velocity. I'm not sure, but
remember that the inertial stability, it's the square root of the inertial stability, which makes it somewhat less shallow. The other thing is in a real cyclone, the diffusivity increases towards the centre.
So
that compensates somewhat. Yeah. So we have the following differences. I think I've said this. We've got the elongation in the radial direction. We've got the depth scale depends on I and not F. Oh, and the other difference to the classic one is that I've used a drag coefficient instead of the no slip condition. You can actually do the classic Ekman boundary layer with the drag semi-slip condition. It's not very difficult to work out. So if we're going to use the linear model to help us understand the non-linear model, the solutions had better be sort of similar. And these are for the same storm. The left-hand case is the linear model, the right-hand case is the non-linear model. And you can see that we've in fact got the decrease in the depth towards the centre. We've got the wind maximum, it's less supergradient. The reason it's less supergradient is that we've removed vertical affection in the linearisation. The updraft tends to be a bit broader than in the non-linear model. But even things like the transition from frictional descent to frictional ascent, you know, that's present in both models and at somewhat similar radii. The peak inflow is not as strong. That's probably partly because we've removed the U to UDR term in the linearisation, but it's also because we've got K constant with height, and you tend to get somewhat stronger azimuthal winds and weaker radial winds because K is larger right near the surface, and so we're mixing momentum down to the surface more efficiently in the linear model. That keeps the swirling flow strong, and with the swirling flow being strong, the gradient wind imbalance is less, and so we get less flow. This is the other way of looking at it, and the thick grey line is the gradient wind. The closely spaced dots are the boundary layer mean azimuthal wind. The other filled dots are the 10-metre wind, so you can see there's a difference in those. The updraft is the thin solid line, is reasonably similar in both cases, and the open circles give you the 10-metre radial wind. So it's reasonably consistent between the two. If we plot just profiles near the radius of maximum winds, the blue is linear, the red is non-linear, and you can see that in both cases we've got something that looks rather like an Ekman spiral. It doesn't go back to 0, 0 because of the semi-slip condition. The non-linear model, the spiral tends to be wider, and you're seeing stronger supergradient flow than you are in the linear model. So one of the things that surprised me when I first did this, so I remembered back to when I was an undergraduate student and studying meteorology, and you do the boundary layer course and they teach you about the Ekman spiral, and then the next thing the lecturer always tells you is what a terrible approximation the Ekman spiral is and how you almost never see one in reality. And yet, you know, here we are proposing, and if you look at photographs from drop zones, they actually look quite like an Ekman spiral. So is Ekman-like dynamics reasonable in a tropical cyclone? Well, the sort of things that mess it up in the normal atmosphere, baroclinicity is often one, and due to thermal wind equation effects, you can have the wind turning in either direction with height. Another one that often messes it up in the real atmosphere is the turbulence structure is very complex because you've got strong thermal effects on the turbulence. Whereas in a tropical cyclone, there's no diurnal cycle, so you haven't got the boundary layer growing and decaying as the stability changes. And the turbulence is predominantly shear generated, so the diffusivity is actually quite simple. Another factor which I think helps keep the dynamics close to being Ekman-like dynamics is that the boundary layer is very shallow because of the inertial stability term. With a shallow boundary layer, there's less opportunity for things like direction, baroclinic shear to upset the structure. And the fourth thing that makes it more realistic is that we've used a semi-slip boundary condition rather than no slip. Limitations, I think I've mentioned most of these. One limitation is that the linearization doesn't work if you've got a storm that's close to a Rankine vortex, because then the inertial stability is 0. The motion form of it only has wave number 1 asymmetries, which I've ended up not showing you. And we've also got to assume the translation speed is small if you read the paper. The turbulence closure is very simple, but these are, we should keep these limitations in mind, but the model is helpful for interpretation. So why does the boundary layer vary with depth, vary with radius? Here's the figure from the, this is the same storm as I showed you before, but calculated with the linear model. And the white curve is my rule of thumb 2.5 delta, which you can see is indeed increasing with radius. And if you remember the flow from the nonlinear model, that's about the height of the rate of flow being 0. Why does the surface wind factor vary with radius and azimuth? Well, you can calculate the surface wind factor from the linear model, and it comes out to be this term. And I now have to remember what I plotted here. Here is my summary of the storm. So we've got the vertical motion, radial and azimuthal surface flow. This is the inertial stability, in this case going from 2 by 10 to the minus 3 down to about 10 to the minus 4 out here. The parameter chi starts off with 0, it increases very rapidly and is roughly constant at about 0.5 outside the radius of maximum winds. And that gives you, if you plug that number into here, this gives you the calculated surface wind factor, about 0.8 in the linear model. That's a little bit higher than in observations for the reasons I've mentioned, but increasing very rapidly up to 1 inside the radius of maximum winds. So this is largely a reflection of the fact that the boundary layer is becoming shallower, and with a shallower boundary layer, there is more opportunity for transfer of momentum down to the surface. Why is the frictional updraft near the radius of maximum winds? This is perhaps one of my favourite explanations in here. If we insert the solution, so the calculated U flow, into the continuity equation, and we integrate vertically with height, we can calculate what the updraft at the top of the boundary layer is. So this is essentially Ekman pumping in a vortex. And we get this expression here, which is in my 2001 paper. When I wrote that paper, I didn't actually realise what an interesting equation this was. But if you compare that to the classic Ekman equation, this is the classic Ekman expression, so it's 1 on F times the curl of the stress. And the classic Ekman theory is done on an F plane, so we could take F inside the curl operator. And now let's compare these two expressions. This bit that's circled is simply the curl operator. This is curl in cylindrical coordinates, in axisymmetric cylindrical coordinates. This is the surface stress. In this case, it's actually it's linearized, so the full form is CD times V plus V naught all squared, but that linearizes out to being this. So we've got curl of the surface stress In the classic theory, we divide by Coriolis. Here, we've divided by the absolute vorticity. So it's actually a very close cousin of what Ekman worked out 108 years ago. Ekman's spiral was his PhD thesis, by the way, if you didn't know it. He started his PhD and his professor said to him, I think he arrived for his first day as a student, and his professor said to him, we want to understand why icebergs, when they move, don't move with the wind direction. They move at an angle to the wind direction. I think that would be a good PhD project for you. And the legend has it that he went home that weekend and pulled out his notepad and wrote down some equations and came to his professor on Monday and said, "Here, I've solved the problem. What do you want me to do for the rest of the 3 years?" If we take this expression for the tropical cyclones and expand it, so we simply apply the product rule of differentiation, we break it into two terms. And we can plot those two terms. So what we've got here is, in the blue curve, is the total updraft. This is for the same vortex as I keep showing you. The red curve is this first term. Now this first term looks like the vorticity gradient times the stress. So it's 1 on vorticity squared, vorticity gradient times the stress, and that's the red curve. The green curve has got the stress inside of the derivative. So this term is actually the curl of the stress term. So if you were naively adjusting the classic Ekman ideas, you might say, well, we'll take the curl of the stress and we'll replace vorticity by F, and you get the green curve. That actually looks nothing like the updraft that you get from the model. And in particular, you don't really get a strong maximum. You don't get a broad updraft. You've got descent in most of the area because the curl of the stress is actually negative. So it's actually not very accurate to say that the updraft in a hurricane is proportional to the curl of the stress, because it's the vorticity gradient term that dominates and gives you the updraft to a good approximation. Yes, so the main updraft is the vorticity gradient term, and therefore the maximum updraft becomes near the vorticity gradient. And I haven't got the slide I thought I was going to have you have next. You remember the slides I showed you before where I plotted vorticity, and we had the fairly constant vorticity within the eye, and then the gradient of vorticity across the eyeball, and then the skirt. So the maximum gradient of vorticity actually occurs across the eyeball. And that is why you get the strongest updraft near the eyeball. In the linear model, the strongest updraft actually occurs slightly outside of the radius of maximum winds, and in the non-linear model it's slightly inside, which is an important difference. Another one of my favourite little results in here is, let's just consider what happens if we replace the semi-slip boundary condition with the no-slip boundary condition. And this was another very good paper that was quite old. It was published by Eliasson in a special issue of the Journal of the Metsoc of Japan in 1971. But he showed that if you had a laminar boundary layer, so a no-slip surface boundary condition, then the updraft is constant everywhere within the eye. So for linear friction, you basically don't get an eyewall. If you want to get an eyewall, you need to have quadratic friction, or the semi-slip boundary condition, which is what you get in the turbulent boundary condition. And then within the eye, W increases linearly with radius. And have I got a plot of W somewhere? Yes. on the magenta curve here. For the semi-slip boundary condition, you've got W increasing linearly with radius, and then it changes a bit when we get into the transition zone. Okay, I haven't actually shown you the leading to this, but I think I'm just going to have time to do it. Here are two storms, and these are both somewhat like Rankine vortices. In each case, the maximum wind is 40 metres a second at a radius of 40 kilometres, and I'm sorry I've got different axis scales here. I didn't notice when I plotted them until it was too late. So the vorticity in the eye is the same in both cases. And in this one, we have a very narrow skirt. So these are modified Rankine vortices. V is going as r to the minus alpha. And I should have put the equation on and I didn't. So V is going as r to the minus alpha. This is r to the minus 0.8. And this one is r to the minus 0.2 is the power law of the gradient wind. So in this one, we are fairly close to a Rankine vortex, and in a Rankine vortex, we have zero vorticity except within the eye, whereas in tropical cyclones, we have a skirted vorticity extending out to large radius. The most dramatic difference, and these were calculated with the nonlinear model, I should say. The most dramatic difference is the updraft. This one, we've got close to a metre a second. This one, we've got about a third of a metre a second. But if you look at larger radius, we've got essentially no updraft except at the eye. So the air is coming in and is accelerating so fast as it comes in. The radial flow is much more peak in this case than in this one, that even though we've got convergence because it's coming towards the centre of the storm, it's actually coming faster and faster towards the centre of the storm, and it doesn't turn and head upwards until it hits the eyeball. So we've got, in terms of the angular momentum budget, what's happening in this case is we've got quite a strong radial gradient of angular momentum. And so as the air particles move in, you remember the dynamics are that they are losing angular momentum to surface friction, and to first order, that angular momentum has to be replaced by radial advection. So in this case, UdMdR is about the same as UdMdR in this case. But dMdR is large, so U is small. Here, dMdR is small, so U has to be large. And so we get a stronger inflow and much stronger updraft concentrated in the eyeball in the peaked case. If we look at radius height sections of them, we can see this one is a relatively small storm, peaked wind profile, very strong updraft, essentially zero updraft at larger radius, whereas this one we have a weak updraft, but we have a broad area of ascent coming out to large radius. This one has a weak outflow aloft, whereas this one has a relatively strong concentrated outflow aloft. And here's the same computation with the linear model. Again, we're seeing probably about 4 times as strong an updraft rather than 3-to-1 ratio. And so it's really the difference between the radial gradient of angular momentum that has a big effect on how the storm looks. And that's this radius height sections for the linear model. In fact, we've got weak descent for the peak profile, where we've got descent everywhere for the flat profile. And I might actually, I think I've said everything in these slides, so I might actually skip over this bit because there's one more interesting thing to look at. Yeah. I should have remembered what was in my slides because now I've got figures that show it better. At the radius of maximum winds, the wind speed is the same, so the loss of angular momentum is similar in both cases, which has to be balanced by U, D, and UR. But here, we've got large D and DR, small d and dr, so we get large U in the peak storm, small U in the flat storm. So if you think of a storm that's, particularly a storm that has undergone rapid intensification and has become, they often become a very heavy profile. They get a very strong idle updraft. So there's perhaps almost a positive feedback here, I don't really know, between boundary layer convergence and the storm structure. Interstorm variability. This is some work I did a few years ago, and I have never quite tidied up and published. But this is, I think, this is quite neat. So it's inspired by James Franklin. Nice figure. And what I did was, for each of these storms, I took the flight level aircraft data on the day, and I calculated a mean radial profile of the wind. So something like we've seen here, some were flat, some were peaked, they had different radii of maximum winds, different intensities. And then I fed those profiles into the nonlinear model. Put those, ran them in the nonlinear model, and then compared the eyewall profiles. And you should probably just concentrate on the blue curves. The red curves have got a very crude calculation of the warm core effect as well. But the blue curves are straight out of the model. So this one was Brett, which had the lowest and perhaps the most marked wind maximum. This one was Dennis, which had a relatively strong wind maximum and quite a broad one. The height scales are the same in both cases. This one was Bonnie, which had relatively weak supergradient flow and a very broad jet maximum. Floyd was a bit stronger, a little bit more peaked than Bonnie. Georges was quite subtle differences between these that are produced by changing the flight. I think are explained by the differences in the flight level winds. And last of all, we get Mitch, which was the very peak storm and quite markedly supergradient. So I'm certainly not explaining all of the variation, but there is a tendency for the model results to be systematic with the differences between storms that James Franklin had found 10 years ago.
So how did you calculate the particle profile of this wind?
These are taken straight out of the model. So what I did was James had averaged all the dropsons together. I didn't have to do that. But when the plane was flying figure fours through the storm, I took all the radial flight level wind data, which was mostly at 700 millibars, some of them it was a bit higher, and I just averaged those all together. And so I averaged them together and had an azimuthal mean flight level wind profile. I said, I calculated the pressure field from that, the axisymmetric pressure field using the gradient wind equation, and I ran the model.
So you non-linear
Or non-linear.
Non-linear. So
Yeah.
what causes the difference between? In other words, which term of your non-linear model will cause
It's one of the things I have to do is go back and run them through the linear model. It's a good question, but it's these sorts of differences. It's the difference in the inertial stability of the storm. Brett, which was this one here with the very low maximum, Brett had a very small eye, and because you had it to get to the same maximum wind with a smaller eye, the vorticity in the eye is much higher, and Brett had very, very high inertial stability in the eye. So the scale depth, which is proportional to 1 on the square root of the inertial stability, means that the wind maximum in Brett comes out to be very close to the surface. So this is work in progress, and just for the last few minutes, and hopefully in a year or two I will finish this off and write a paper.
I will forget today.
But I think, you know, I think it's quite a nice explanation of what's going on, and you know, this is really quite a big difference from one storm to another, and it doesn't seem to be. There's been there was a paper by Roger Smith and Mike Montgomery that had some discussion of different turbulence parameterizations and their effect on the shape of the wind profile. But you know, I don't think that's a very good explanation, because the physics of turbulence should be the same in every tropical cyclone. And now we know that our turbulence parameterizations are not perfect, but it's difficult for me to believe that, you know, the YSU scheme should be best in George, and the Lewis scheme should be best in you know, Dennis, and someone, and you know, Amelia Yamada scheme should be best in Floyd. Really, there should be one scheme which is best across all storms, and so I think this explanation in terms of the radial profile is probably a better explanation.
Could you elaborate the explanation on warm core experiment?
Oh, the warm core. Okay, these were very crude, and I definitely need to do these calculations more carefully. You'll see that, you know, the top of the boundary layer in these cases is probably somewhere around here. It's a little bit above the wind maximum, and yet you can see there's still significant wind shear aloft. And there's two reasons for that wind shear. One is that the storm is warm cored, or one way of looking at it is the storm is warm cored, but the other one is that the eye wall is not vertical. And so the eye wall slopes out. We know that the slope can vary from being nearly vertical to quite flat. When the planes fly into a storm, one of the things they're trying to do is estimating intensity. So they try to drop the drop song into the strongest surface winds, which means they tend to drop a lot of the songs inside of the flight level radius of maximum winds, so that they fall into it near the surface. And as a result, you get an increase in the wind speed going down because the song is falling. The radius of maximum winds slope like that, and the song is falling down into it. And I just did a very simple, took an estimate of the radial temperature gradient from flight level winds, and based on that, I worked out roughly what the baroclinic component of the wind shear should be, and I simply added that on. So it was very, very crude, because these ones are sort of showing up between 10 and 30% stronger than flight level wind, and that was a bigger difference than I was getting from the model. So I think it's the shape that is more significant. The model is probably still a little bit underdone. You know, Dennis was, in some cases, Dennis was 30%, and we could look more for I don't quite get close to 20. But I was also fairly rough with the way I put the flight level data in. I need to go back and do that more carefully.
Excuse me, is this figure indicate that the wind should have the largest frictional amplitude?
Sorry, which one should have the large?
Wet.
Red.
Wet should have the largest frictional amplitude.
Yeah, I think so. I can't actually remember for sure, but I think you're correct.
The profile indicates that it should have the largest frictional amplitude.
Yeah, it's got very marked supergradient flow, which is suggesting that it's quite non-linear near the surface. So the inflow, the near surface inflow, is probably very strong, and it was a very small eye. So if you think of the continuity equation, you've got a U on R plus the UdR term in there. So the 1 on R factor probably gives you a very strong updraft in your breath.
On the lower area.
Yes.
Near surface.
Yes.
With maybe the high potential difference potential temperature.
Possibly. I'd have to go back and drop signs to check, but yeah, quite possibly. That's a good point. You're all getting me inspired to finish this off, which is good. We've talked about that, so we'll cover that again tomorrow. So the only thing I had thought of covering, and I won't, is there was a little bit of discussion on